Hello, I'm Kunal, and today we're going to solve the problem yet another tree problem. And this has been a part of the December 2021 long challenge. The difficulty level of this problem is medium, and for prerequisites, we need a knowledge of auxiliary tree and disjoint set units. We'll first start with the problem statement. So, we are given some story here, and the problem starts here. You are given a tree with n vertices and weighted edges. So we have a tree, something like this, and the edges are weighted. So every edge would have one weight attached to it. It is rooted at vertex 1. So this vertex will be indexed 1. Now define a function g which takes u and v as parameters to be the maximum weight of an edge on the shortest path between the vertex u and the vertex v. So let's say the vertex was u here and the v vertex was here, then the path this will be taken into consideration, and the shortest path simply implies the single path. So there can be many paths like this, but we want the shortest path. The shortest path will only be this, and we wouldn't visit this node. So this is a simple problem statement defining method. Now G u comma v gives us the maximum weight on this path. So let's say here it's 5, let's say here it's 10, here it's 7. So we have to output 10 since it was the edge with the maximum weight in the shortest path. So it is saying that just calculating G u comma v is too easy, well, which is. So you have to process Q queries. In each query, we are given k distinct vertices. You have to compute the sum of g values of each pair of vertices among these k. That is this value. So what is this value basically? So in this earlier tree, if let's say we have three vertices given and k is equal to 3, the distinct vertices are this one, and this one. So we have to output the sum of g u comma v of all pairs. So one pair is this, so this one path, then the other pair is this one path, then the other pair is this one path. So we are given k vertices and we have to find g u comma v, the sum of g u comma v for all pairs. And it is mathematically denoted as shown here. We are also given that the input and the output are very large, so we have to use fast IO methods. We will now discuss the input and output format. So as we can see here, the first line will contain a single integer t denoting the number of test cases. So there are more than one test case in a single test file. The first line of each test case contains two space separated integers n and q. So there would be 1, 2, up to t test cases here, and each test case here would contain the first line n and q. Then the second line will contain n minus 1 space separated integers, p2, p3, pn, where pi is the parent of vertex I. So let's say this was our tree. Remind you that it was rooted at the vertex 1. Now the parent of 1 is not there. So they have given us the parent of 2, parent of 3, and so on. With this line, we can represent the tree easily. Now, the third line contains n minus 1 space separated integers, w2 to wi, w2 to wn, where wi is the weight of the edge between vertices I and pi. So it's self-explanatory again. Somewhere here, if we are given that this vertex has this as parent, then the same index wi will give us the weight of this edge. The next q lines contains query you will have to answer. So the q queries will be here. The ith line contains an integer ki followed by ki distinct space separated integers. So the ki will be here and it will be followed by ki distinct vertices here, going from v1 to vk. Now the output format is given us. For each test, we have to print one line containing q space separated integers. The ith of these integers should be the answer to the ith query. So all of these queries for one test case will be answered in a single line. So we will have to output t lines. The constraint is that the test cases only go up to 3. So we don't have to see anything there. The n goes up to 100,000. The parent index pi goes from 1 to I. It is just as expected. The weight goes up to 10 raised to power 6 multiplied by 5. The number of queries go up to 10 raised to power 4. The number of distinct vertices in each query go up to n. And our vertex index would obviously go from 1 to n. All vi are distinct. We are given that. It is guaranteed that the sum of ki over all queries does not exist or exceeds 1.5 into 10 raised to power 6. It is also guaranteed that the sum of q over all test cases does not exceed 3 into 10 raised to power 4. Now, if we calculate the brute force time complexity, the g function alone might take order of n. Since it will have to traverse the whole tree to find the maximum weighted edge in the shortest path. Then k vertices, and for each pair we have to find the value of g. That might take us order of k square times n. Now q such queries of k vertices given we have to calculate the function g. That will take us order of q times k square times n. Now this is clearly not feasible given the limits of n, q and k. We'll have to find out that what trick we can use to simplify this problem. Now we'll quickly discuss an example. In this example, we are given a single test case where the graph is of 10 vertices and we have to answer 2 queries. The set P and W is given here and we have drawn the graph on the right hand side. Now for the first query, our k is equal to 4 and these are the 4 distinct vertices. So to mark them, it is 1, 5, 4 and 6. So this pair, its answer will be 60. For the pair of 1 and 6, the answer will again be 60. For the pair of 6 and 4, the answer will again be 60. For 5 and 4, the answer will be 50. For 5 and 1, the answer will be 50. For 1 and 4, the answer will be 40. So to sum it up, the answer should be 320, which is given here. For the second query, k is again given 4 and these are the 4 vertices, 2, 3, 7 and 8. For 8 and 7, the answer is 80. For 8 and 2, the answer is again 80. For 8 and 3, the answer is 80. For 7 and 2, the answer is 70. For 7 and 3, the answer is 70. For 2 and 3, the answer will be 30. So to sum it up, the answer should be 410, which is also given here. Now we'll start with our solution. So first of all, we'll see the case where we just have a single query. The query is represented on my left and here the value of k is 4. The distinct set of vertices is 1, 4, 5, 6. We've already seen that the answer for this should be 320. Now we have to get the summation of g, u, v over all the pairs of vertices in this set. We're calling the set S. Now there are 2 ways to get the solution. First is to basically enumerate all the pairs and then find the maximum edge with some sort of range max query. And then after we find a max weighted edge, we sum it over all the pairs. The second solution, however, is to focus on the edges. The question is, we take an edge with weight 30. We ask that in which pair would this be the maximum weighted edge of the shortest path? We'll start by taking the edge 20. So if I take this edge, I have the set S. I find that in which pair would this be the maximum weighted edge? In this case, I find that 20 cannot be the maximum weighted edge in any pair. For 1 4 there will be 40, for 1 5 there will be 50, and so on. So the contribution of 20 in this summation would be 0. Now for 30, it will also be 0 since it wouldn't be the maximum weighted edge in any pair. For 40, we find that we have this one pair in which it is the maximum weighted edge. So its contribution would be 1 time in this equation. Now for 50, we similarly find that there are two pairs. One is 5 comma 1, the other one is 5 comma 4. So the contribution of 50 is twice. For 60, the pairs would be 6 comma 1, 6 comma 4, and 6 comma 5. So its contribution would be thrice. Now we see that the sum of this would be 320, which will be equal to our solution. Here the other edges like 70, 80, 90, 100 will be similar to the contribution of 20 and 30, that is 0. Now we will discuss the method with which we can come up to that answer. That is, for each edge, we can find its contribution C in this equation. So for that, basically, we'll use the data structure algorithm of DSU. What we'll do is, initially, we take this disconnected tree in this fashion, and we'll try to connect it. Now, how will we connect it? We'll first of all list the edges in a non-decreasing form. And we'll start from the left. We'll first put this edge in the tree. So the edge 20 will come somewhere here between 1 and 2. Now, initially, these all are individual sets. So this set is of vertex 1, this set is of vertex 2. With this set, we will also maintain a count, let's call it CK, and in that count, what we'll store is the number of vertices of the set which also belong to our original set S of k vertices. So in this case, the set 1 contains one vertex, that is 1 itself, from the original set. Mind you that our original set was 1 comma 4 comma 5 comma 6. So here CK was 1. Here CK is 0. So when we add an edge, what we do is basically we take two sets with many vertices and connect with an edge. So we will be joining all the special vertices belonging to S from here to here. So we will get a new number of pairs P, and that number of pair will be connected by this edge. And let's say its weight is W. Then the contribution of this particular edge inside our equation here would be P times W. Now to find the number of pairs, we simply have to find the number of, let's call it set 1 and let's call it set 2. We'll simply have to find the CK of 1 and multiply it with CK of 2. This is self-explanatory that we choose two special vertices and we connect them. So here 20 is the weight of the edge and the contribution is 1 times 0, that is 0. Now this has become one whole set and its CK remains 1, since 1 is the only vertex in the set. Now we add the edge 30. With this edge, we are adding 3. Now, this set had a CK of 0 since 3 doesn't belong to our special set S here. So, the contribution again will be 0. And then this will become one set and CK of it will remain 1. Now, this whole is a one single set. Then we'll add the edge 40. That is here. When we add 40, we see that here the set was 4 and its CK is 1 since 4 belong in our special set. So this gives us the contribution of 1 times 1, that is 1. Next edge will be 50. We have added these 3 edges. Next edge is 50. We will add the 50 edge here. And here was our vertex 5 with CK 1. Now, mind you that this whole set has become 1 now. And this set includes 1, 2, 3, and 4. The CK for this set have gone 2 because of 1 and 4. So now since CK of this is 2, this is 1, then the contribution of 50 will be 50 times 1 times 2, that is 50 times 2. And then this whole will become one set. And its CK will become 3. Then we'll add the edge 60. Here 6 is there with CK1. So the contribution of 60 will be 3 times 1. When we finally sum up, we have the contribution of 40 times 1, 50 times 2, and 60 times 3. So we get 320. Now, what good has happened here? Let's say the number of edge was E. Basically, in a tree, E would be n minus 1. That is order of n. Now, for each edge, we have just used a DSU operation. And DSU operations cost order of alpha of n. Now, the total complexity of this would be order of n times alpha of n. This is much better than our previous estimation of n square pairs times n. So this has been a great improvement. Now, since we have discussed the solution for just a single query, where for k vertices, we were able to solve our problem in n times alpha of n. Now, if there are arbitrary q queries, and for each q queries, we have a different k. If we run this algorithm, then we get a time complexity of order of q times n times alpha of n. Now, this time complexity is still not feasible. But we are given that the sum of k over all test case is almost near the range of n. We can make use of that. What we'll do is, if we are given k vertices in this tree, let's say we have 1, 4, 5, and 6, what we do is we decompose this tree into a shorter tree, which is known as auxiliary tree. This auxiliary tree is basically closed under the operation of LCA. What it does is it removes the useless vertices and contracts the edges such that now, since 3 was not useful in our calculations, what we'll do is we'll shorten this whole path into just single edge, and the weight of the single edge will be the maximum weight in this path. So here it will be 50. So the auxiliary tree for this would look something like starting with 1, an edge of 20, then 2 with connected with 4 with an edge of weight 40. Now this 2 and 1, from here it will be connected to 5 with an edge of weight 50, and this will be connected to 6 with an edge of weight 60. This whole here is again useless and it would not be there in our auxiliary tree. Now you'll notice that we haven't changed the answer, but we have minimized the tree somehow. This is also known as a virtual tree, since this is giving a sense of virtuality. We are skipping the vertices in between of these paths. Once we have this tree, we can theoretically prove that the number of edge in this tree are less than 2 multiplied by k minus 1. The edge is not less than or equal to this. If we achieve this size of tree, we can execute one single query in the time complexity of order of k times alpha of k. Now this construction of auxiliary tree also takes order of k times log of k. The final time complexity would be this summed up with this. It will end up being this itself since this is less than this. Now after that, for all queries, it will take a sum of this. So we can see that we can complete one query in O n times log of n. Now since we have achieved this time complexity, we also have to sort the edges in each query. So that can go up to q times log of n. So the final time complexity would be order of n plus q log of n. And this is feasible for our problem. The time limit for our problem is 4 seconds. So that will incorporate this alpha of k in that. So we don't have to worry about that. Finally, we'll see how we can implement this whole method in our C++ solution. Now we'll start with our C++ implementation. First, we'll start with our main function in which we have started with the fast IO configuration since it was demanded in the problem statement. After that, we input the number of test cases, and for each test case, we initiate the solve routine. Inside of the solve routine, we first take the integer n and q as an input. Then for each vertex from 1 to n, we first clear out the graph entry. The graph entry of each vertex will contain the adjacent neighbors of that vertex. The DSU parent will also be initialized to -1. So all the vertices will remain as independent sets. After that, the special count, which I was mentioning as CK in our approach, this is initialized to 0. After that, we take input the parent of all vertices, and in the graph array for parent I, we store I as its neighbor. After that, in a separate weight array, we store the weight of all the parent edges. After that, we also have to find depth of each vertex in the original tree. Depth of the vertex 1, which is the root of the tree, will be 0. The parent of 1 is kept to be 1. Now the weight of 1, that is the weight of 1 and its parent vertex is kept to be 0. After that, we have maintained two arrays, maximum and ancestor. The ancestor array will actually keep record of the ancestor at logarithmic level. So it will store the ancestor at the first level, then ancestor at second, then ancestor at fourth, eighth, and so on. Similarly, the maximum array will store the maximum weighted edge between the vertex and its logarithmic ancestor. This whole computation will be required to compute our auxiliary tree. After that, we have kept the global variable timer to be 1. This will be required for the Euler path, and we then initiate this DFS routine, which essentially calculates the depth of each vertex and also the out time for the Euler path. After that, for each query, we first start taking k as input, and then we maintain an array vert of all the k vertices, and we take the input of them. After that, we have maintained a set of vertices, and this whole logic is basically used to compute our auxiliary tree. The auxiliary tree is stored in the compressed edges array. In this, we basically store the weight of an edge and two vertices of that particular edge. And we get the auxiliary tree inside the compressed edges array. After that, we initialize the DSU special count of the independent set which contains the vertex I to be 1. Vertex I is one of the k vertices given in this query. After that, we start with initializing our answer to 0. And we sort compressed edges in a non-descending fashion. Then for each edge, we combine, first of all, the edge 1, the edge 2. That is the first vertex of that edge with the second vertex of that edge. And we provide that the weight of the edge is edge 0. Now I'll show you the combine routine. In this, what we do is we find the set of u and set of v. Then we have this logic to enhance the DSU construction. And finally, we compute the return value. That is basically the contribution of this edge weighted w when we combine two u and v sets. We also have to merge these two sets. That is being done here. So what we do is we merge the v set with the u set, and we increase the special count of the u set with what was there in the v set, and we finally return this value. This value then returned is added in the answer itself. We output the answer, and then we clear out all of the data locations we have used. These data locations will again be used in the next query. This way, we have solved our problem, and it is being done for each test case. Thank you for watching the video.